All right, everyone. Today we're going to be looking at the notes entitled Exponential Growth and Decay Models Day 1. And I guess this would be the culminating piece for us on this unit, just doing a bunch of applications with exponential growth and exponential decay, seeing all different types of variations on the models that we've been looking at, and just basically at this point we have all the algebraic skills to kind of manipulate them and work with them and so forth. So that's exactly what we'll be doing. This should probably help you with the challenge that's going to be assigned. You can use this notes worksheet and the following one to help you along with that. Remember, you are allowed to use a partner if you would like with this, if you are so inclined. So anyway, let's get started here. It says there is a relationship between the mortgage amount, the number of payments, the amount of payment, how often the payment's made, and the interest rate. And the following formula illustrates this relationship. So I have this piece right here, and as you can see, it is a very, very complicated formula, but it does have that exponential piece right in here. And so let's see what the variables represent. Let me keep reading here. P is the payment, so in fact that's what we're going to calculate for. R is the annual rate, represented as a decimal. M is going to be the mortgage loan, what we take out. T is the number of years, and N is the number of payments every single year. So we're going to look at my scenario for our house. My wife and I did initially take out a 30-year home mortgage loan for $188,000 at a fixed rate of 5.75%. This is definitely the case. We were fortunate enough to put quite a large down payment on our home, and this ended up being the loan that we needed to take out. And let's see. Actually, this is somewhat outdated as we refinance because the interest rates are so low, but that, I guess, is besides the point. But anyway, we're going to take a look at this scenario. So if this still held, if we still had the 30-year loan at this amount at 5.75%, what was our monthly payment? So let's put it in first. Let's kind of just see how it plays out, and then we'll go ahead and let the calculator do most of the work for us. We're just going to be extra careful here. So let's see. R times N on top. So the interest rate is going to be 5.75. The mortgage loan, what we took out a loan for from the bank, was that amount right there, $188,000. And then kind of down on the bottom here, let's see what we have. I'm going to put monster parentheses here. Let's just make sure I've got this. And then another set right in here. So 1 plus and 0.0575. And let's see, rate or over N. So by the way, monthly payment, so it'll be 12. And then raised to the negative, and then N it looks like is going to be 12 again, times 30 years. Probably have to put that in parentheses. And again, kind of that piece right there as I'm looking at it. And then on the back end, divided by, it looks like 12. I'll tell you what, take a look and see how that plays out for you. I'm just putting in the numbers from example 1 into the formula. The trick is going to be getting it in the calculator as well. But in this particular case, again, it's a 30-year loan. We pay every month, so 12 payments per year. We took out $188,000, and the interest rate is 5.75%. So let's take a look. Let's bring up the calculator and give it a try. So I have this right over here, and we're going to be super careful with the way we type this in. As you can see, it's quite complex. But I like exactly what I did on the board here in terms of parentheses. I think I'm going to add one more set of parentheses, just kind of looking at it. Not sure if it'll matter, but I want to err on the side of caution there. So around the exponent, I probably will put in parentheses. But let's see what we have. Okay, everyone, so let's start typing. If you can beat me to this, that's great. But let's see, what was our monthly payment? So 0.0575 times 188,000. Okay, close that off. Now let's start on the bottom. The bottom is going to be the killer here. And so let's see, I've got parentheses, 1 minus, and then I'm going to do another parentheses. You can see that little compound interest type sort of show up in this formula, the 1 plus R over N to the NT. It's just a little variation on that. But 0.575, there we go, divided by 12. Okay, keep it going here. I'm going to raise that. And again, I'm going to put parentheses around that negative 12 times 30. Let's see if that should play out. Okay, got that. It looks like I'm going to need to close off some more parentheses one more time there because of this piece from, I wanted to put the whole bottom in parentheses, so I started out a parenthesis, and so I do have to end with the parentheses right there. And then I'm going to hope for the best here and just divide by 12. So take everything there and then divide by 12. Well, everyone, it looks like the moment of truth. Let's see if it played out the way we wanted it to. And that looks great. As a matter of fact, that was precisely what we paid when we opened up our loan with this bank and we started paying off the mortgage. So $1,097.12. That was it. $1,097.12. Okay. Well, that's awesome. So here's what's kind of interesting about this. There's a part B, and again, this was just utilizing a very complicated exponential model here, just putting in the numbers, quite frankly. But a nice application of exponential models regardless. But here's what's kind of interesting about this piece. So we took out, again, this is sort of old and outdated, but that's okay. We took out a 30-year loan, and we would have to pay this amount every single month for 30 years. And so there's a second part to this. It says at the end of the loan, how much would we have paid in interest? And by the way, again, this assumes something that most people don't do, but this assumes that we would not contribute extra principal over the lifetime, like trying to pay down the mortgage as much as possible. And again, we certainly did that. And plus, again, we refinanced, so this is not the case anymore. But what would happen if we just paid this amount every single month for 30 years? How much would we have paid above the $188,000? So remember, we only took out $188,000 from the bank. But by paying this every single month for 30 years, how much more than $188,000 did we pay? So let's see. Let's do this. Let's do the 1,097.12, again, times 12, so 12 payments per year, and then times 30 years. So really times 360. That would be the case here. So times 360, that's how many payments we would make over the lifetime of the loan. And let's see what happens. So I'm going to do that 1,097.12 times 360 and take a look. So $394,963.20. Let me see if I can get that. 394,963.20. So again, if we just paid that amount every single month for the 30-year period, we would have paid the bank $394,000, almost $395,000, when we really only took out $188,000. So if you think about this, the bank, if I subtract away the $188,000, how much did the bank make on our loan there? Well, as you can see, quite a bit. So let's go ahead and subtract the 188,000, and look at that. So the bank only loaned us $188,000, but made a profit of about $207,000 as a result. So that's what's kind of interesting about that piece. You're not just paying off what you take out, you're paying all that interest and quite a bit of money. All right, so if we only paid this amount every single month, we would have paid this much in interest above and beyond our loan. Wow, that's crazy. All right, good problem. Just kind of thinking it out there, just trying to find different applications for exponential growth and decay, and that's certainly one that works nicely. All right, let's go into the next piece here. And so I think I've alluded to this before, of course, that basically there are two forms of exponential growth and decay models, and you can see them both on your paper. We've been working mostly on this one right over here, the one on the left, y equals a times b to the x, and we will probably still do most of our application with that. I think that is the best model for all these applications. I think it's a very straightforward model to work with. But here's kind of the scenario, is every exponential model in base B can also be written in this uniform base of base E. And we saw sort of a context for that when we dealt with compound interest, and that looked great. As you get into some of the higher levels of mathematics, a lot of the work you will probably end up doing will be in this base E right here. Some of the calculations you do are quite a bit easier and a little more efficient when you work in base E. But again, for our purposes and the way that I've designed this unit, we'll probably do most of our application in base B. But again, they're really, you can use either or and come up with the same results. So I guess let's fill in a few of the blanks and then just kind of take a peek at them and just see how they coordinate together, and then just do a couple more examples together. So really everything you do in the exponential model in base B revolves around that base B. So if you remember correctly, basically I would categorize that B value as really the effective rate. It truly is the growth or decay rate in a time period. Let's do per time period here. Okay, so by what percentage did it increase over the course of a year? By what percentage did it increase in any particular time period? That will be given by that B value. So again, the effective rate is really that B, the true growth rate over the course of a time period. Now again, this base E model, again, works really nicely. Again, a lot of good algebra there that goes with this. Can work nicely on your calculator with the natural logarithm and so forth. So definitely some good stuff with that. But you'll see the matchup here. So I guess just because it looks a little different, we want to be clear on what each part represents. And so here's what I have. That A sub 0 is really just what's called the initial amount, or the initial quantity. So put that in for me there, the initial quantity. T represents the number of time periods, of course. Okay. A would be the amount after T time periods, so the dependent variable basically. Again, T and A, those will represent the two variable quantities. So the amount after T time periods. And then that K, the best way to sort of describe it is what is called the continuous growth and decay rate. So remember, we kind of talked about this before. When we used base E, we talked about something being compounded continuously. And that's sort of the measurement that goes with this piece right here. Really, I guess the best way to describe it, if you kind of think about that compound interest formula, and by the way, this really is just that compound interest formula. This is just PERT, just now applied to quantities outside of just being money. So here's your principal, so to speak, your initial amount. Here's your base E. Here's what I would call it is the nominal rate before being compounded continuously. So that's that R value. And then obviously the T on the end. So it's really just the PERT formula there. So this K, I guess for lack of a better description, if you can relate it to that, it is just that interest rate. It's just it's the percentage before being compounded continuously. And then once you apply that base E, it's basically what's called the continuous growth or decay rate. Okay, so just sort of put that piece in. And what you'll see with this, again, a nice thing with working with this, and we've seen this before, if K is positive, it's growth. And if K is negative, it's decay. Again, you won't have to do too much with that piece. You won't have to really create too much with this, so you certainly can. But as I said, my emphasis is typically on the y equals a times b to the x. I like that model better. I think it's, in my opinion, more efficient for what we do, and I think it's actually more accurate for what we do. So anyway, let's go ahead and take a look at the rest of your paper here, and then we'll do the remaining examples. It says every exponential model in base B can be written in base E, and every exponential model in base E can be written in base B. And so if I put one of these models on top of the other, you can see how they coalesce pretty nicely. So I'm going to do exactly that. And you can write this or not write this. We'll obviously put this piece in momentarily, the relationships. But let's go ahead and just write one on top of the other so you can kind of see it. And again, there should be a little continuity with what we've talked about in the past, especially that compound interest piece. So if you sort of look at one on top of the other, it's tough for me to circle without it making it too convoluted here, so I'll just kind of do this. You know, these two things represent the same thing, the dependent variable. Here, these two values, they're the same thing. That's the initial quantity. If I come over here, everybody, the x and the t really represent the same thing. It's the number of time periods, the independent variable. So if you kind of look at it, these two match up, these two match up, the x and the t match up. So the only thing that's left to really put the two models together is the fact that b is really the same as e to the k. Those two values are identical. So that's exactly the piece that you're going to put in right here. And we have seen this before. When something is compounded continuously, basically what that means is that is the true growth rate over the time period. That's b. So that's just the relationship that we're going to take a look at here. Really not a whole lot, to be honest. But you know, if I give you a model in base E, you can work with it. And if I ask you to translate it over to base B, yeah, sure, theoretically the algebra would allow you to do that. So e to the k is the same as b. All righty. Well, let's go to the next page here. And as I said, let's just do a couple examples with this. So here's what I have. Example 2. The exponential growth of a colony of bacteria can be modeled with the function. N is measured in grams, and T is measured in days. And what's the population after 5 days? So again, what we do is we have this colony of bacteria growing exponentially. And so we have this equation in base E that will model the number and the time frame. And so remember, the idea really is very simple. If I give you an input, you can give me an output. And if I give you an output, you'll be able to give me the input. So let's check this out. Again, we have the foundation to be quite successful with this. So let's do this first one right here. Let's make sure I've got this. So 80 times 0.045, and that's that k value, and then times 5. And so let's just grab the calculator there. And you know, I think you could pull this one off without my help. But everyone, if you get an opportunity, can you please type in 80 times e raised to the 0.045 times 5? And I have it on my calculator as well. I have it on my paper, I should say. I've got about 100.19 grams. And that's apparently what it was measured in. Good. So again, that one, sort of an introductory problem there. Just if I give you the input to the function, you can come up with the output. And base C, again, is quite easy to work with on the calculator. You have that primary button to help you compute it. Okay, well, let's get B. Then after how long will the population double? So in this case, I have a feeling we're going to solve for T. And so I start out with e raised to the 0.045 times T. And in this case, remember what each little value represents, and then I think you've got a good shot at this. In this case, I'm going from 80 probably to 160 in terms of the doubling. And notice what happens here. In essence, that initial value is sort of irrelevant, because if I just ask how it's doubling, this comes over anyway and just becomes that too. It's really this that's going to determine how long it doubles, not the initial value. I could have started with a different number and asked the same question, and we would get the same result. It's really the 0.045 that's going to determine the doubling time for this case. And so it looks like what I probably want to do here is take that e. Again, we just came off a lesson dealing with exponential equations. So everyone, let's take that e and roll it on over to the other side. Here it goes. Rolls on over. And when it rolls on over, of course, it becomes the natural logarithm of 2 equals 0.045t. And you can see, again, one of the benefits to working in base E, I think I referred to this yesterday, is that you can get this from the calculator nice and easy. So everyone type in ln of 2 for me and divide by that 0.045 when you get a chance. And if you do that, it looks like we're getting something along the lines of about 15.4 days. Okay, good. Now, as mentioned, basically there are just two different ways to represent exponential growth and exponential decay. There's the base E model, which was given in the problem, and there's also a base B model. And so let's go ahead and see what we can do here. The relationship between the two I gave you above, so this is the first time with us doing it together, but it basically says e to the k is equal to B. And there we go. That e to the k is actually a number. And remember, we've done this before. This is sort of the limit of the effective rate for any nominal rate, in this case 4.5%. And the way I guess I would read this from a compound interest perspective, this would be 4.5% compounded continuously. What would be the true growth rate over the time period? In this case, it would be days. So what would be the true growth rate every single day, from one day to the next day to the next day? By what percentage would it be growing? So that's how I would argue this piece right here. And let's see what we end up getting. If you end up doing, sorry, hang on just one sec. There we go. For some reason that popped up. Never mind. Okay, so, oh no, not again. And let me just see here. Okay. Well, I'm going to continue. Sorry about that. Let's see if this will still work. All right. Phew. And so let's see. We end up getting B equals, in this case, I think I have it there. Oh, okay. So I've got about 1.04603. So if I calculate a B value, and I do that e to the 0.045, and you please do it on your calculator and verify it, but basically you should get this number right here, which would mean, of course, this is a 1 plus the percentage. So every single day, I guess the argument can be made that it grows by 4.603%. Good. And again, just two different models to talk about the same thing. And I've got n equals then, starting out with 80. And this would be our growth rate, our effective rate, so to speak, our B value. And then raised to the T. So again, just working with the two different models there. If you can go back and forth with it, great. That's all I'm really looking for. But as I said, most of the application that we will do will be in base B. All right. Please let me know if you have questions along the way. Otherwise, we'll go to the last example here. And let's see what it says. Oh, perfect application. So the world's population in the year 2000, and I got this online, this is what's called a mid-year estimate, was, as you can see, just over 6 billion. In 2010, the world's population, again a mid-year estimate, was about almost 7 billion. And so based on that, with the population growing exponentially over time, it says write an exponential model in base B for the population in that period of time, and what is the effective annual growth rate. So basically, by what percentage would the population be increasing from one year to the next, to the next, and to the next. So let's see what we have going here. I guess what I would encourage you to do just to start it out, and again, this is not a true necessity, but I think it's helpful. I would just start it out as y equals a times b to the x, and let's see what we have, and let's see what we're going to solve for. So I guess the argument can be made. We are going to start our model in the year 2000, and that initial population then, as a result, was this piece right here, 966,429. All right, so some crazy numbers here, but I think we can still work it. So that's going to be little a. It doesn't say anywhere in the problem as to how fast it's growing, by what percentage or what the growth rate is or anything like that. I think, everyone, that's the unknown. But what I do have is basically an ordered pair that goes together. I have an input and an output for this particular function. And if I have the input and output, I can use it in the equation to solve for what I'm missing. And in this case, what I see is in the 10th year of this model, that population now has increased from just over 6 billion to just under 7 billion. So I have 6,848, et cetera here. Let's see if I can get this all in. 929. So I hope everyone's okay with that piece right there. That seems to be what our model would suggest. And then as a result, obviously, as you all know, I need to find a B value if I'm going to write this model. So I'm going to bring this calculator on up, and let's give this a try. A lot of numbers to type in, but I think this should work out all right. So do it with me if you would, please. So I've got 6,848. 932,929, and I'm going to divide that by 6,082. 1.12966,429. All right, hope I got my numbers all correct there. And I'm going to go ahead and hit enter on that piece, and I get 1.1259 essentially. I'm going to go ahead and write as much of that as I can remember. So 1.12592. So 1.12592, give or take, and that equals b to the 10th. And again, I'll probably do a little better on the calculator there, actually getting a little more precise. Not that it'll matter too much. And so I guess the question then becomes, how do I get the true growth rate? By the way, this would actually represent the growth rate over the 10-year time span. And as you can see, here's our 1 plus the percentage. So I guess the argument could be made that over 10 years, the population of the world has increased by about 12.59%. Pretty interesting. But what I'm looking for, if we're going to write the model, is not by what the growth factor is over 10 years, but what it is every year. And we've seen this a couple times before. I told you you're going to do all sorts of roots here, all sorts of bases of logarithms. In this case, it's definitely the root. I probably want the 10th root on both sides of this in order to pull this off. And so let me go back to my calculator here, and I'm actually going to type in the number 10. I'm going to go to the Math menu and hit that X root. And then I'm going to hit second and an answer. That would be down here. So it gives us that. No, it didn't do that on here. That's interesting. Well, I guess I'll type it in manually. So if you get a chance, looks like this calculator doesn't want to do that, but that's all right. I'm going to type it in 1.125919896. That's all right. And so I've got that piece right there, and let's go ahead and hit enter on that. And that, everybody, should be our true growth rate. So 1.01193. 1.01193. Excellent. Alrighty, so let's write this model, let's answer the question, and move on to that next piece here. Doing great. So I have y equals, or you know what, sorry, scratch that. Let's do p equals for population. That makes better sense. And this lengthy number right here, yikes, so 6,082,966,429, and this will be times 1.00. Oops, sorry about that. Let's do that again. So 1.01193 raised to the t. Okay, I think that is our winner right there. In terms of the growth rate, again, this is our 1 plus the percentage increase. So this would be 1 plus 0.01193. And I'm hoping everybody agrees with me then that it would be 1.193% if I move that decimal over 2 to the right from there. So 1.193%. So every single year in this time frame, that's what the population is increased by. Excellent. Alrighty, let's just reverse it because, again, part of this particular notes worksheet is dealing with the two models, base B and base E. Again, I like base B, but base E you will certainly see over time. So let's get you comfortable algebraically with that. And guys, before we continue, let's just go ahead and write e to the k equals b. Let's get that scenario taken care of. In this case, I have the b value. So 1.01193, and that's e to the k. So as you can see, the base e, that uniform base, is right there. What I want to do is solve for k. And you can see this is just where the variable is the exponent. So I have a feeling you would all agree with me that I'm going to take this base e and roll it on over to the other side. So just going from one model to the other, in this case, I probably just want to take the natural log of that number over there. And so let's do exactly that. I'm going to bring my calculator up one more time. And I'm going to go ln 1.01193. And hit enter on that. And you can see it's just a touch lower than the 1.19%. It's at about 1.859. And so that's going to be our k. Let me just make sure I've got that. 0.01185 or 86. Let's bring that calculator up one more time. Let me see it. So about 0.86. Okay, good. And again, you can keep going. Actually, what you would find, working in base E, you do want that k value to really go as long as possible. In this case, I'm probably cutting it off a little too soon. But that's all right. I think for our purposes here, it should suffice. So everyone, let's go write this model. Got to write that long number again. So 6082,966, everybody, 429. And it's e raised to the 0.01186t. Now both models should suffice here, solving for part C in this problem. And it says, use either model to extrapolate when the population could reach 8 billion. Now again, I like most of the work in base B, so if you don't mind, I'm going to do that. So everybody, it looks like we're going to have to write the whole thing. We'd love for it to have been in billions and maybe shortchanging a little of these population estimates, but that's what it is, guys. There's your 8 billion right there. So scary thought, but when could the population theoretically reach 8 billion if the growth rate continues on its present course? So let's see. Let's solve this last one together. So 082 again, 966, 429. And again, I'm going to use that base B. And in this case, oops, I'm sorry. We know base B. So let's put that in. So 1.01193 raised to the t. Alrighty. Well, guys, we're going to solve that one. If you can beat me to the punch here, that's great. I think you would all agree that we're going to divide by this number right here, bring that on over, and then we're going to solve for that variable momentarily after that. So let me just make sure I've got everything lined up here exactly the way I want it. And let's go calculate. I've got 8 billion. Yikes. And then I'm going to divide by that number there one more time. 082,966,429. Okay, and I'm going to hit enter on that. And bear with me on that, but I have about 1.31514. So it looks like 1.31514. And then at equals 1.01193 raised to the t. Alrighty. Now I'm going to probably have to come over here a little bit. So hopefully you have a little more room on your paper. But the question, of course, now arises, how am I going to solve for this variable? I think we're just about a step away here to pull this off. And everybody, I think we're going to want to roll this on over to the other side. So get it ready. Roll it on over. And when you roll that on over, as I said, good things are going to happen. The t is free as can be. And I should get a logarithm with now that base. Again, when it rolls over, it becomes the base of the logarithm, 1193 of 1.31514. I just need to verify my number there. I'm just going to bring the calculator up one more time just to make sure. 1.31515 officially. So I messed that up just a little bit, but I think that's not too bad. Okay. Well, last step. Told you you're going to be dealing with logarithms in all sorts of bases. This is a number stored on your calculator. You just need to be able to access it. Those who have the TI-83s, you're going to do the change of base formula. If you've got the 84 pluses, I believe, you can go ahead and put that in. But I'm going to do mine for one last time over here. And here we go. So log of the input. So log of the 1.315. I'll go 15 here just because I'm able to now finally. And then divided by the log of 1.01193. Hit enter. And there we go, everyone. So in about 23.1 years, that seems to be the case. And so in about 2023. Wow. So some really fascinating stuff that you can do with exponential modeling. Here are some applications of it, of course. We're going to do some more applications on the day 2. And you're going to be doing some applications on that challenge, of course. As I said, please feel free to use any notes that you need. Use a partner if you'd like, whatever the case may be. And explore some pretty good modeling. Well, again, thanks for listening, and please let me know if you have any questions.